Our final speaker in this session is Nathan Cruze. He is also at NASA Langley Research Center. And I guess I should have said that, all of this session are both my colleagues and my friends. And I think that's a good sign of collaboration. Somebody asked about different disciplines, and I'm not sure which one came first, colleagues or friends. But Nathan has his Ph.D. in Interdisciplinary Studies from The Ohio State University, right? Definitive article, right? Okay. And has a bachelor's degree in economics and mathematics, a master's degree in economics and statistics. And without any further ado.
All right. Thank you all. So I want to acknowledge my colleague, Kate Ballard. She's a fellow statistician in my branch. And we're going to speak a little bit about some of the statistical challenges and thinking that underlies our community testing right now. And I'm not seeing my slides on the screen. Thank you. There we go. So that's a little easier. Just in brief, we'll share a little bit of history about the 1960 studies that informed the current ban over supersonic flight over land, and contrast that a little bit with our risk reduction studies. And then I'll point to some of the statistical thinking in both the response, or the y-axis, the dose, and their combination through some regression modeling. And we'll try and draw some conclusions about future needs and have some discussion. So a lot of the work on sonic boom was conducted in the 1960s, and you can see a couple different studies in St. Louis, as well as Oklahoma City. I think Paul Borsky was the name. He was a statistician at the National Opinion Research Center. And you can see some of the survey efforts there in terms of the number of interviews and even some efforts to re-interview the same. You can also see something about the number of exposures in each of those places. And pity Oklahoma City, right, with 1,200 booms. I'd also point you to an interesting study in the vicinity of Edwards Air Force Base. This was a psychoacoustic study where they even went to lengths to try and build mock housing units, representative, so to speak, of a home in the Midwest, which might be a part of the country a little more apt to be exposed during a transcontinental flight, supersonic flight. There was also an interesting 1960s assumption about who was most likely to be in those homes, and so the sample skewed majority women in those cases. Fast forward to 2011 and 2018, NASA conducted some risk reduction studies using an F-18 aircraft in a special dive maneuver. And when you contrast these, you can see a lot of repeated measurement of the same study subjects. And so what I'd invite you to consider is that there in the white space, there was a lot of evolution in the statistics literature, that the tools for analysis of longitudinal survey data evolved over that time frame. So it's not just the engineering technology that's changing, it's the statistics technology that's changing too. And we'll point to a couple aspects of that. I think this gets back to a question that was posed earlier about could we use citizen science in some meaningful way? And the answer is, well, maybe, but let's start with a basic research question, like, did you hear the aircraft? On the right, you see the curated data from our recruited sample at Galveston, and you can see the balance of data across the 5 categories there. That primarily they were not at all annoyed, and about 56% of all captured responses indicated they couldn't hear it, even though they agreed to be in the survey. And so to me, that's kind of a compelling case for continuing with this line of research. On the left, you see a persistent map, I think, from the last day of testing using the citizen science portal, if you will. And what I'd point you to here is that there was kind of a traffic light indicator, quiet, medium, and loud, and the preponderance of the data here show kind of an attitude that the sounds were medium or loud, and so this could be one example of a selection bias. And all of this is to say that the way we sample matters. This is part of the justification for randomization in assigning treatments in experimental design, as well as random sampling in the conduct of a survey. And so why spend the time motivating that? Well, in one important part of our sampling activity, we're not doing random sampling. And so we talk about site selection, but this is in fact part of the sampling activity. There would be something like 4,000 airfields nationwide, but by the time you copy and paste the aircraft requirements onto that, it quickly shrinks to about 4 dozen feasible test sites nationwide. And so we made the survey statisticians from WestStat cry uncle, and instead of doing any sort of random sampling, we're being purposive, being very deliberate about the sites that we visit. And along with that, you have some very important things to consider. Our colleague Will Dobler presented related work at last year's DataWorks, but his recent Journal of Aircraft paper points to differences by geography and climate zone about kind of the mean loudness and the variation in the loudness. So it behooves us to go to as many different places as we feasibly can. And in that process, you're dealing with the demographic makeup of the sites that you get to visit. So it's interesting that our discussions about prospective flight paths also include the demographic composition of the populations underneath. Even kind of consolidating that information is a large task. And I'll point out a recent presentation at an Acoustical Society of America by Joe Check, one of our lead contractors, that discusses kind of the geospatial processing that goes into that site selection. But one of the key takeaways is that in the determination of where we will test, that's a purposive rather than a random sampling decision. Okay, so nobody blink here. We'll see if this animation works. Thump, thump. And maybe one highly annoyed or two highly annoyed here. In this figure, you see kind of a stylized version of our potential sonic thump exposure region, including regions for acceleration and deceleration, and that kind of central rectangle is where we think we can reliably measure the sonic thumps. One important aspect of sampling is defining the population of study. And so you see that in kind of the blue box. That's about a 20 by 30 nautical mile region. And so our population under study will be all individuals in that 20 by 30 region. We're going to assemble a union of census blocks within that region. So we have kind of demographic totals. And then the sampling frame, kind of the list that we'll use to recruit our sample, will be a list of postal addresses. And we can describe kind of a two-stage sampling process. First, you take a sorted list of all those postal addresses, trying to get recruitment materials to a particular household. And then within the household, there's a sampling procedure that will be used. This is due to Rousseau, Brick, and Park, but there are a variety of methods you can use to get a qualified respondent within. And that's important because it means we'll be able to do valid population inference, at least in the affected, in the region under study. One other thing I'll point out here is that our need for near real-time response has kind of influenced our choice of survey mode, or the manner in which we deliver our survey questionnaires. Since the risk reduction studies, there has been experimentation with paper modes in the first study at Edwards Air Force Base, and interactive voice recording modes have been talked about, but they really don't meet the real-time need requirement. The IVR modes might not be effective without callbacks, which add to cost. So really, this is going to funnel our data collection through internet and smartphone-based modes. Shifting our thinking a little bit to the dose axis, the x-axis here, we can point to a couple different ways that statistical thinking enters into the equation. And namely, we have to know that a sonic thump has taken place. And so this is something of a classification problem that we have. We have a goal to detect at each sensor location whether or not the sonic thump has been heard by the machine instead of the human this time. And so this is an example of the contractor team working with government-furnished information in the form of template waveforms, as well as even information about prospective algorithms. And they came back to us within their requirements and proposed a method based on computed cross-correlation when compared to a template waveform. So you see kind of the picture of the classifier off to the right there that's going to use this correlation coefficient as well as the loudness of the event to try and separate out what the signal was and whether we classify it as a sonic boom, sonic thump, or otherwise. There's some information in Blaine Harker's recent Acoustical Society presentation, but what I'd point you to here is a fairly high accuracy or prompt detection of sonic thumps in kind of this simulated case, and excellent true positive and false positive rates here. I'll be very interested in seeing if we can replicate that during the phase 2 and the acoustic validation. One thing that struck me here, just kind of listening into the contractor team, they were asking about assumptions. Could we always assume that a sonic thump should be present, or are we going to have to operate on buffered signals or things of that nature? And so it struck me that there was really an interplay between our tolerance for type 1 and type 2 error in some of our decision making on the dose estimation side. Aaron shared a little bit about the Kalman filter approach that's going to help us fuse together a physics-based model with live measurements taken throughout the area. There have been some comparisons to NASA work by our colleague Jake Kloss using interpolation and kind of the prevailing thinking on the spatial Kalman filter by Blue Ridge Consulting here. Aaron mentioned that we can use it to produce the geolocated estimates of dose for the single event, as well as produce measures of uncertainty in that case. With the cumulative dose, we have an interesting challenge here due to the nonlinearity. And so while we can get the point estimate for the cumulative dose fairly easily, getting a variance estimate for the cumulative dose is a little bit more of a challenge. And so what the contractor team has proposed to do is use some Bayesian statistical modeling using kind of the independent or the individual single event doses and their estimates of uncertainty, and using Bayesian models to propagate that through in the cumulative dose response model. It's probably worth emphasizing, though, that what we have are estimates, that they are subject to some degree of uncertainty, and that figures into some of our decision making on the regression modeling side as well. This kind of pulls together the survey response on the right-hand side, as well as the doses on the left-hand or other right-hand side. This is from the Galveston study in 2018, and again, we had something like 5,000 captured responses from 371 individuals in this survey effort. You can see that a large number of them could not hear that the testing was going on. And moreover, the phenomenon that we're interested in, the highly annoyed, is a very small proportion of the data. Really, 1% of all reported cases constitute highly annoyed responses. The histograms of doses that we capture at any of our future test sites may differ to the extent that we could concentrate doses at different levels of the testing range. But what I think I would point out here is that within our nominal 70 to 87 decibel window, a lot of the responses in Galveston kind of fall within that. And so when we apply dose response modeling to that, we start to get a flavor or a sense of what we might see at future testing. So kind of working our way toward the regression modeling that we intend to do. This is a reproduction of work that one of Dr. Allison Wilson's students did, Jasmine Lee, in a 2020 publication. But we're specifying a Bayesian hierarchical model to fit this regression model. And so you're specifying combinations of conditional and marginal probability relationships, and turning the Bayesian crank, as they say, to produce resulting point estimates and measures of uncertainty. You see some of the tabulated results there. Kind of the main effects, the beta naught is a general intercept, as well as the slope, which is indicative of the rate of annoyance in response to dose. This is a conditional or subject-specific model, though, and so I think Aaron mentioned that that's one thing we could do. It's not quite the object we're interested in producing for the IKO, though. What we really want is a marginal relationship, so one that's not dependent on any one subject-specific attitude, that's more indicative of the population or the probability of annoyance among the population at large. And so along the way, there's been experimentation with modeling methodologies that allow this. Aaron's done work on generalized estimating equations, for example, and comparing some of the alternatives here. Right now, our current way of thinking is to fit that subject-specific model and then integrate with respect to the distribution of random effects to get the marginal relationships that we're ultimately interested in here. And this would be more closely akin to what we would want to provide to the IKO at the end of the test. It's important that we acknowledge uncertainty in the doses, and it has kind of a profound impact, especially if we have a high degree of uncertainty around our estimated doses. Namely, it contributes to an attenuation bias, or kind of this flattening of a dose-response relationship that you see depicted here. And so it's well understood, especially for logistic regression, that this contributes to the possibility of underestimation of annoyance or overestimation of annoyance, depending on what part of the dose range that you're working in. We're probably most concerned with a tendency to underpredict, especially as it's related to some future policy decisions. This has been an area of emphasis in some of our research team's output, as well as points of interest among the acoustics literature. And I think it's something that we're continuing to develop in our research agenda internally. There's plenty more that we could say about composing a nationally representative dose-response curve. One technique that's available is this idea of multi-level regression with post-stratification. One use case for that is for adjusting so-called non-representative samples. And so this may be akin to our use for it, where we have to combine, possibly disparate dose-response curves from 4 to 6 communities and produce something that is nationally representative. We're also concerned with the rarity of the event that we ultimately want to measure, namely high annoyances should be an infrequent occurrence, especially if the technology works as intended. And so we're taking stock of methodologies that deal with this, that help us make sure that we're not tending to underpredict annoyance in the communities that we visit. And it's also worth mentioning that we have a fairly limited testing range, dose range that we're operating within. And so I think just collectively, a lot of these regression techniques would be making sure that we're not omitting or failing to account for potential lingering sources of bias in the estimates and the models that we produce. We also have, kind of budget-constrained resource problems. We want to make sure that the dose designs we propose really maximize the amount of information that we'll get from each sortie, from each flight that's conducted in the area. And so this is kind of a rich research agenda for us and potential collaborators. Hint, hint. I did want to highlight something that my colleague has worked on extensively. Kate Ball has shown a lot of leadership as we try and meet the IKO needs for potential certification. So if there comes a day where supersonic commercial aircraft are a thing, the FAA and other regulatory agencies will need to verify designs meet that case. And so what I'd point you to here, Kate knew to reach for the IDA handbook for some guidance on how you could validate, say, a predictive model with limited measurements. And so presently we're looking at this trio of hypothesis tests or exploring opportunities for equivalence testing. And we may have some related needs at NASA during the acoustic validation phase as well. In conclusion, I hope to make a case that statistical thinking adds a lot to our community response testing. This goes from the planning of the campaign to the execution of the analysis we want to do, and even beyond. I think there's some similarities to operational test and evaluation. We can point to the number of constraints that are present in what we want to do, and just pose some rhetorical questions about how it is we can be assured that the results that we produce will be fit for the policymakers, recognizing that we are not the policymakers ourselves, and how we choose to communicate any limitations or any of our choices to the affected stakeholders. And I do hope I've pointed to a variety of areas for continued research, and that it prompts some discussion here as we conclude. I've got several pages worth of references if you're inclined. And since this is a workshop, I did want to share a template code. Some of the data is available with Jasmine Lee's paper for download. And since you've learned about Bayesian models at this workshop, why not try it out for yourself? All right, thank you.
Thank you, Nathan. Questions?
So great talk, Nathan. I've got lots of questions, but let me just ask one.
Sure.
So the whole purpose is to associate, data on the tails, so dosages on the tails with, again, tail-valued responses. And my concern is that when you fit a dose-response curve of various sorts, it may not extrapolate well in those places. So have you thought about quantile
regression,
Bayesian equivalence, and so on?
I think that would be a fruitful line of research. I think we've had some discussions about even under what circumstances we would be willing to extrapolate, and you see kind of this very narrow 4%, 5% annoyance among the community. I think some of this we're also kind of grasping for what the regulators themselves ultimately need. We haven't been given a stated threshold. You have to investigate out to 10%, out to 15%, and if we knew that, maybe you could design the study a little differently. There is some trepidation on the dose range itself, on the maximum dose that we could deliver. It's not a matter of we can't measure things that loud. It's maybe more a matter of can we continue conducting these tests without one angry call to a congressperson or things like that would shut the testing down altogether. And so right now we are in that limited range, and the quantile regression might be one methodology to counteract that.
You mentioned that you're trying to estimate the probability of annoyance as a function of the dose. It seems like you need to then link each response with the dose that they received. And I'm sorry if I missed it.
Mm-hmm.
How are you doing that directly? Are you estimating that, or is there some way you don't need that?
So I thank you for that question. So the Kalman filter approach basically allows us to estimate dose on a fine grid of latitude and longitude. And then from the survey app itself, the respondent will be asked to indicate their location. And so there will be a couple kind of usual candidates, home and workplace. But within the app, WSDA has experience with travel surveys, for example. They can basically drop a point on a map and say, I was here at said time. So as long as that functions from the survey app, you have a latitude and longitude that you can match to the estimated dose. Now you are counting on the respondent to accurately identify their location at the point in time, and not do any sort of telescoping where they confuse the sequence of booms, or make sure they're really focusing on the time in the prompt. But I think when the internet and survey app modes will facilitate that well. When you consider things like paper, I think that's a lost cause. And even for phone, trying to indicate where you were at a point in time over the phone would be a real challenge. So that's kind of shaped our thinking along the survey modes, and been an important part of working with the contractor team to kind of pull these separate pieces together. The dose estimation with the survey through a IT infrastructure.
Other questions? So, Peter?
My mission manager is going to grill me.
No, just wanted to add that in terms of measuring the exposure, we will have an array of, I think Aaron touched on it, we'll have an array of sensors across the test area, and we will also have a prediction based on models for that data. So the test data anchors the prediction, and we use the prediction to more precisely make an estimate of the dose at the location where the person is, as Nathan said.
Back on the issue of the location, I noticed in your Galveston plot,
Mm-hmm.
you had a couple of points in the water. Were those boaters, or was that airs? Or my iPhone sometimes says I'm in the middle of the Potomac River, so I don't.
Well, in fairness, if you zoom way out on that map, you can actually find a couple points off the coast of Africa. I think there was some engagement with the mariners in the area. So depending on where they were at that point in time, maybe someone logged in. Otherwise, maybe there's fumbling around with the map. It just reflects conditions, I think, on that last day of testing. So I couldn't tell you whether there's some gross error there or someone was actually in the water.
Question. Back across. This is a rather athletic moderator role. I'm going to tell you. Toss it across.
As a kind of follow-up on that, is there something that prevents you from using GPS locations on somebody's phone for reporting?
Especially if you can opt out or turn off tracking within the app. That's problematic if they turn it off. You have concerns about uptake with the phone app itself. We still want to encourage the use of internet if you don't have a smartphone device or choose not to use it. Furthermore, I think there is some privacy concern that persistent tracking for government survey, that sort of thing. But those kind of combinations of concern, we won't get it all. We know we can't get it all from GPS on a smartphone, for example. Oh, well.
We got time for one more quick question. Anybody has one? What's that?
Very nice talk. I guess I had a question about the dose model. Mm-hmm. So you guys have sensor array outside, which tells us what the noise level is outside, but mm-hmm. every house is insulated if I have the window open. So that probably has quite a lot of uncertainty comparing your models of what the sound is given your array that's laid out versus what the person actually perceived. And so I'm guessing, how do you guys handle that? Is that just like plus 10 decibels?
And this is an excellent question, and one that my esteemed colleague Pete Parker has been asking us about.
Thank you for that question.
I think what we can feasibly estimate is the dose outside. We won't have direct measurements, accounting for transmission loss indoors. We can ask some questions both on the background survey about the structure of their homes, and so we might have some covariance information there. And then I think Aaron highlighted some of the questions that we're asking. We can ask about, one, were you indoors, so we can know presence, were they indoors or outdoors, whether they had the windows open or not. And so we can get some information probably in the form of like fixed effects in a model rather than really precise measurement close to their ears.
Okay, well, great. Well, thank you all very much for coming and for your participation. Let's thank all the speakers again.